Hello, I'm Damla Senol-Kali. Today I will be presenting our work, GenASM, a high-performance, low-power approximate string matching acceleration framework for genome sequence analysis. Genome sequencing, which enables us to determine the DNA sequence of an organism, plays a pivotal role in areas such as personalized medicine, outbreak tracing like COVID-19, and the understanding of evolution. Modern genome sequencing machines extract small randomized fragments of the original DNA sequence, which we call reads. State-of-the-art sequencing machines produce either short reads or long reads. Read mapping is the first key step in genome sequence analysis, where we take each read, align it to one or more possible locations within the reference genome, and find the matches and differences between the read and the reference genome segment at that location. Multiple steps of read mapping must account for the sequencing errors and for the differences caused by genetic variations. As a result, read mapping must perform approximate string matching or ASM. However, it is currently bottlenecked by the computational power and memory bandwidth limitations of existing systems. Our goal in this work is to design a fast and flexible framework for both short and long reads, which can accelerate multiple steps of genome sequence analysis. To this end, we propose GenASM. We base GenASM on BiTAP, an ASM algorithm that uses only fast and simple bitwise operations, making it amenable to efficient hardware acceleration. To our knowledge, GenASM is the first work that enhances and accelerates BiTAP. We modified BiTAP to support long reads and to enable parallelization. We also developed a novel BiTAP-compatible algorithm for traceback, and we co-designed specialized hardware for both algorithms. GenASM is flexible and can be used to accelerate multiple use cases. In this work, we evaluate three of them in detail: read alignment, pre-alignment filtering, and edit distance calculation. We find that for all these three use cases, GenASM is significantly more efficient in terms of both speed and power consumption than state-of-the-art software and hardware baselines. Let's look at approximate string matching and the Bylab algorithm in detail. As I introduced, read mapping is the first key step in genome sequence analysis. When we are mapping the reads generated from the sequence genome, they may not exactly map to the reference genome due to genetic variations and sequencing errors. As we can see from this example, these errors and differences, which are also known as edits, can take the form of base, deletions, substitutions, or insertions. Since multiple steps of read mapping must account for these errors, they must perform approximate string matching. The goal of approximate string matching is to detect the differences and similarities between two sequences. In genomics, ASM is required to determine the minimum number of edits between two genomic sequences, which is called edit distance, and also to find the optimal alignment with a traceback step, where we find the sequence of matches, substitutions, insertions, and deletions along with their positions. Approximate string matching is typically implemented as a dynamic programming-based algorithm, which has quadratic time and space complexity. Therefore, it is desirable to find lower complexity algorithms for ASM. One candidate to replace DP-based algorithms for ASM is the Bylab algorithm. Bylab uses only fast and simple bitwise operations to perform ASM, making it amenable to efficient hardware acceleration. Bylab tackles the problem of computing the minimum edit distance between a reference text, such as a reference genome, and a query pattern, such as a read, with a maximum of k errors. The algorithm has two steps. Bylab starts with a pre-processing procedure where we generate one pattern bitmask for each character in the alphabet, which are A, C, G, T in our context. These pattern bitmasks help us to represent the query pattern in a binary format. Second step, which is search or edit distance calculation, is the main step of the algorithm. Here, we examine each text character one by using the pre-processed pattern bitmasks, status bit vectors, which are updated at each text iteration and hold the partial match information for the text characters examined so far, and the simple bitwise operations. I won't get into the details of the algorithm, but let me highlight three key properties of it. First, Bylab iterates over each text character as the outer loop, and it iterates over each possible edit distance, 1 to k, as the inner loop. So when we have long error-prone reads, both of these loops need to iterate over very large numbers. Second, there is two-level data dependency in Bylab. So first, there's an outer loop data dependency when computing deletion, substitution, and match bit vectors, as they require old R bit vectors, which are coming from the previous text iteration. And also, there's an inner loop data dependency when computing the insertion bit vector, as it requires RD-1, which is coming from the previous inner loop iteration. And another property, Bylab generates these four intermediate bit vectors, deletion, substitution, insertion, and match, but they are not stored and processed with a traceback step to find the optimal alignment. So we find that Bylab has 5 limitations that hinder its applicability and efficient hardware acceleration for genome sequence analysis. We have already covered the first 2 algorithmic limitations, and we find one more algorithmic limitation, which is no support for long reads. In Bylab, the query length, so the read length, is limited by the word size of the machine running the algorithm, because each bit vector has a length equal to the length of the pattern, and we perform the bitwise operations on these bit vectors. Thus, the algorithm does not support long reads whose lengths are on the order of thousands to millions of base pairs. So these are the algorithmic limitations of Bylab algorithm. Even after we solve the algorithmic limitations of Bylab, we find that we cannot extract significant performance benefits with algorithmic enhancements alone. For example, while Bylab iterates over each character of the input text sequentially, we can enable text-level parallelism to improve its performance. However, the achievable level of parallelism is limited by the number of compute units in existing systems. We would expect that a GPU, which has thousands of compute units, can overcome this limitation. However, we find that a GPU implementation of the Bylab algorithm suffers from the limited amount of memory bandwidth available for each GPU thread. And these are the hardware-related limitations. In order to overcome these limitations and design an efficient accelerator, we find that we need to both modify and extend the Bylab algorithm and also develop specialized hardware that can exploit the new opportunities that our algorithmic modifications provide. To this end, we propose GenASM, an ASM acceleration framework for genome sequence analysis. To our knowledge, GenASM is the first ASM acceleration framework for genome sequence analysis, and it is also first that enhances and accelerates BiTAP. We make significant modifications to BiTAP in order to overcome those 5 limitations. First, we modify the BiTAP algorithm by extending it to support long reads and by eliminating loop-carried data dependencies to enable parallelization. Second, we develop a novel BiTAP-compatible algorithm for traceback, which uses information collected during ASM about the different types of errors to identify the optimal alignment of reads. These cover the algorithmic contributions of GenASM. And third, we co-designed specialized low-power and area-efficient hardware for both algorithms, and this covers the hardware-level contributions of GenASM. Our first algorithm, GenASM DC, is the modified BiTAP algorithm for distance calculation, where we extend it to provide efficient support for long reads, and we enable parallelism besides bit parallelism that baseline Bylab provides by first performing loop unrolling and removing the loop dependencies, and second, exploiting text-level parallelism, where we divide the text into overlapping subtexts and search the query in each of these subtexts in parallel. Our second algorithm, GenASM TB, is a novel BiTAP-compatible traceback algorithm, which walks through the intermediate bit vectors generated by GenASM DC and finds the optimal alignment. In order to decrease the memory footprint of the algorithm, it follows a divide and conquer approach, where we divide the text and pattern into overlapping windows and perform the traceback computation for each window. After all of the windows' partial traceback outputs are generated, we merge them to find the complete traceback output. Let's look at the hardware design of GenASM. Our co-designed hardware consists of 2 components. First, GenASM DC, which provides hardware support to efficiently execute our GenASM DC algorithm. And second, GenASM TB, which provides hardware support to efficiently execute our novel GenASM TB algorithm. GenASM also has 2 types of SRAM buffers, DC SRAM and TB SRAMs. Let's look at the high-level overview of GenASM. GenASM execution starts when the host CPU issues a task to GenASM with the reference and the query sequences locations. Then, GenASM DC reads the corresponding reference text region and the query pattern from the memory and then writes these to its dedicated SRAM, DC SRAM. After that, GenASM DC divides the reference text and query pattern into multiple overlapping windows, and for each subtext and subpattern, GenASM DC searches for the subpattern within the subtext and generates the bit vectors. Then, GenASM DC writes these bit vectors to the TB SRAMs. Once GenASM DC completes its search for the current window, then GenASM TB starts reading the stored bit vectors from TB SRAMs and generates the window's traceback output. Once GenASM TB generates this output, then GenASM computes the next window and repeats steps from 3 to 7 until all windows are completed. So our specialized compute units and on-chip SRAMs help us to match the rate of computation with memory capacity and bandwidth, achieve high performance and power efficiency, and scale linearly in performance with the number of parallel compute units that we add to the system. Let's look at GenASM DC's hardware design. We implemented as a linear cyclic systolic array-based accelerator using small and very simple logic components. This design helps us to maximize parallelism and minimize memory bandwidth and memory footprint. Processing core is the basic compute component which computes the intermediate bit vectors, and when we add the flip-flop based storage logic around the processing core, we define a processing element or PE. Multiple PEs are concatenated to define a processing block. We have DC SRAM, which stores the reference text, the pattern bitmasks for the query read, and the intermediate data generated from PEs. And we also have TB SRAMs, which store the intermediate bit vectors generated by each PE of GenASM DC for later use by GenASM TB. We implement GenASM TB hardware using very simple logic, which reads the bit vectors from one of the TB SRAMs using the computed address, then performs the required bitwise comparisons to find the traceback output for the current position, and then computes the next TB SRAM address to read the new set of bit vectors. After GenASM TB finds the complete traceback output, which is also called cigar string, it writes the output to main memory and completes its execution. We demonstrate the efficiency and flexibility of the GenASM acceleration framework by describing 3 use cases of approximate string matching in genome sequence analysis. First use case, read alignment step of read mapping, which is the most time-consuming step of read mapping that we align each read to all of its candidate reference regions and then find the optimal alignment. Our second use case, pre-alignment filtering for short reads, where we aim to quickly identify and filter out the unlikely candidate reference regions of each read by approximating the edit distance between them and filtering out if it is an above a threshold. And third use case, edit distance calculation, which is one of the fundamental operations in genomics that measures the similarity or distance between 2 sequences. We believe the GenASM framework can be useful for many other use cases, and we discuss some of them briefly in our paper. Let's look at our evaluation of the GenASM design and framework. We evaluate GenASM using a combination of synthesis of our DCM-TB accelerator datapads and detailed simulation-based performance modeling. We evaluate a 16 gigabytes of HMC-like 3D stacked DRAM architecture with 32 folds. So our accelerators can be ported anywhere in the system, but in order to achieve high parallelism and low power consumption, we place GenASM DCM-TB and the associated SRAMs in the logic layer of 3D stacked memory. As I will show next, our hardware is highly efficient in terms of both area and power, so they are within the budget limits of the logic layer. For the use cases we evaluate, we compare GenASM with state-of-the-art software and hardware baselines. I won't go into details, but you can refer to our paper for more details of our evaluation methodology. We synthesize our DCM-TB accelerator datapads with a typical 28 nanometer low power process. Both accelerators operate at 1 gigahertz, and we find that for 32 GenASM accelerators, one for each HMC volt, total area overhead is 10.69 millimeters square, and total power consumption is 3.23 watts. We observed that both area and power consumption of GenASM at a single volt is around 1% of the area and power consumption of a single Xeon CPU core. So GenASM has low area and power overheads. Let's look at our results for our first use case. As software baselines, we compared GenASM with BWA-MEM, which is shown with red bars, and Minimap2, which is shown with purple bars. Both are commonly used state-of-the-art read mappers. We find that GenASM achieves 648 times speedup over 12-thread run of BWA-MEM and 116 times speedup over 12-thread run of Minimap2, while reducing power consumption by 34 times and 37 times. Compared to Gacktopf-Darwin, which is a state-of-the-art long-read alignment accelerator, GenASM provides 3.9 times better throughput, 6.6 times better throughput per unit area, and 10.5 times better throughput per unit power. For short reads, compared to same software baselines, GenASM provides significant speedup and reduction in power consumption similar to long reads. And compared to Scylla-X of Genex, which is a state-of-the-art short-read alignment accelerator, GenASM provides 1.9 times better throughput while using 63% less logic area and 82% less logic power. So let's look at our results for the second use case. I don't have time to cover this result in detail, but here is the key takeaway. Compared to SUJI, which is a state-of-the-art FPGA-based filter, GenASM is more efficient in terms of both speed and power consumption, while significantly improving the accuracy of pre-alignment filtering. And let's look at our results for the third use case. Again, I won't be able to cover these results in detail, but again, here are the key takeaways. Compared to the software baseline EDLIP, GenASM provides 2 to 4 orders of magnitude speed up while reducing power consumption by 2 orders of magnitude. And compared to the hardware baseline, ASAP, GenASM provides 9.3 to 400 times speed up while consuming 67 times less power. Before I conclude, here is the list of additional details that you can find in our paper. And to conclude, in this work, we focus on approximate string matching because it is one of the main bottlenecks of genome sequence analysis. We propose GenASM, an approximate string matching acceleration framework, to accelerate multiple steps of genome sequence analysis. GenASM is the first work that enhances and accelerates BiTAF for ASM with genomic sequences. In GenASM, we co-design our modified, scalable, and memory-efficient algorithms with low power and area-efficient hardware accelerators. We evaluate 3 different use cases and show that GenASM is significantly more efficient for all 3 use cases in terms of both throughput and throughput per unit power than state-of-the-art software and hardware baselines. Thank you.